Okay, we're going to continue talking about differential equations. There's really nothing new in this lesson except one small little tidbit of information that you need to be aware of, and so you can follow it so you don't have problems in the future. Okay, so differential equations and slope fields. We've done both of those. Differential equations, just a fancy way of saying an antiderivative, looking for that group of solutions for a problem, and slope fields we've been spending the last 2 days on. Just finished an activity with it. This stuff is not important. How many people can drive a stick shift car? Just 3 of us? Well, anybody can kind of drive a stick shift car. Okay. Do you currently drive a stick shift car? So you have one in the family. Cool. Okay, I'm going to skip this because I want to get into the good stuff. But if you recall, when we first started with integrals, we took the antiderivative of a function. We stuck a plus c on there because there was an infinite number of possibilities, which I called a family of solutions. You could also call it a general solution because it's got a plus c on it. One of the things we're going to transition to today is looking for a specific solution. And we saw that when we did the slope fields the last couple days. You draw the slope field, which is the infinite number of possible equations, and then we were drawing specific examples through certain points. We're going to do that today without the picture. However, before we do that, this is a common type of problem that shows up, and they want you to verify the solution. So they give you some weird differential equation. This one happens to be y double prime minus y equals 0, and they want to know, does this function sine satisfy the differential equation on top? In other words, if I take the second derivative of sine, I plug it into the function, I take the sine function and plug it in for y, subtract them, will I get 0? And you've all been doing this long enough to know that I have 2 examples up there, so what can you tell me about those 2 examples? One works, one doesn't. So let's get to the one that doesn't work. Okay. So the sine. Took the derivative first. Derivative of sine is cosine, the derivative of cosine is negative sine. Plugged and chugged it. Negative sine minus sine is negative 2 sine, and negative 2 sine doesn't equal 0. Therefore, it does not satisfy that differential equation. What's the derivative of c e to the x? Say again? No? c e to the x, correct. So it's its own derivative and it's its own second derivative. So without even clicking, we should be able to figure that c e to the x minus c e to the x is in fact equal to 0, and that's why the second one works, like it shows you there. 0 equals 0. Not a very exciting differential equation. Let's get into something more interesting. Okay, so we'll take this function. And in fact, remember that's a derivative because it's dy dx. And so I've been very, I don't want to use the word wishy-washy about this dy dx thing on the left-hand side of that equation. We said it's one way of representing a derivative. The derivative of y with respect to x. Those are called differentials. And what we're working on is a differential equation. So we want to solve that equation just like we've done other ones. I want to know the function that when I take the derivative of it, I get 2x cubed minus 3x. So this isn't anything new. We've done it before. We're just going to throw a new twist in there. And that is we're going to do what's called separating the differentials. The easiest way to remember that is put everything with a y on one side, put everything with an x on the other side. So step 1 of solving this equation is that. And that seems kind of silly. Why do you have to do that? I'll explain why later. Just bear with me. All the y stuff on the left, all the x stuff on the right. How do you get rid of a dx? Say again? Yeah, take the antiderivative of both sides of the equation. That's legal. Because again, remember, we're starting with a derivative, and I want to get back to the original function, so you undo derivatives with integrals. Quick review here. What's the antiderivative of dy? Let me ask my question in a different way. What's the antiderivative of 1 dy? Y. What's the antiderivative of d smiley face? Smiley face. Okay, good. What's the antiderivative of 2x cubed minus 3x? Say again.
8x plus 4 minus 6x squared plus c.
Nope. Half.
X to the lower.
Keep going.
To the fourth minus x squared minus 3x.
Good. I heard enough mumbling in there that somebody eventually came up with enough pieces that I can just click. Okay. Which is good, because now I have the value of the function y is that equation. And if you didn't trust yourself, you could always take the derivative of that and see that it matches 2x cubed minus 3x, but then that's just kind of beating a dead horse over and over again. But notice plus c there. This is a general solution. This is what would generate a slope field. All these different possibilities depending on how c can change. Remember, c can be positive, it can be negative, it can be all kinds of different things. Excuse me. Any problems there? And again, the only thing new there is we're separating the differentials. However, that step is crucial. It's so crucial that I've got that little graphic on there. You must separate the differentials, and I'll show you why in a second. Okay. That was a pretty basic equation. We've done stuff like that. Yesterday on the worksheet, and actually today during the activity, we looked at some different things, some more interesting things. For instance, I brought back this guy. What was that yesterday when you did a slope field? Everybody remember?
Is that a circle?
That was a circle, correct. So now we're going to do the differential equation and show you and confirm that that's a circle. Yesterday when we did it, we just drew a bunch of dashes and looked at the picture. We can actually do the math here to simplify this down to a circular equation. Okay, so step one, separate the differentials. I want everything with a y on one side, I want everything with an x on the other. What's the easiest way to do that?
Cross multiply.
Cross multiply. Beautiful. Okay, decision time. And there's no wrong answer to the following question. Do you want to put the negative sign with the y and bring it over to the left-hand side, or do you want to leave the negative sign with the x? Leave it with the x, okay. You can do whichever one you want. You'll get the same answers. Y dy is equal to negative x dx. Okay. I separated the differentials. Take the integral of both sides. What's the antiderivative of y? Say it loud, say it proud. 1/2 y squared. Technically, I should have a plus c there. But I'm going to be a rebel and not write a plus c. I'll explain why in a second. What's the antiderivative of negative x? I'm writing a plus c on the right-hand side. Well, why? I should have a c on both sides, technically speaking, because I'm getting a general information. But if I move the c to the other side, what's c minus c? C. No matter what you do to c, it's going to stay c. So instead of having to go through that extra step, I'm just going to say, forget about the y's, we'll attach the c to the x term. Do a little bit of algebra here. Whoops. Okay, what did I just do?
Square the 1/2.
No.
Just multiplied by 2.
Multiplied everything by 2, because what's 2 times c?
Yeah.
C. Move the x to the other side. That should look familiar, yes? What can you tell me about that circle? Where is its center?
Origin.
It's at the origin. What's the radius? Square root of c. And so we have an infinite number of possibilities, an infinite number of circles that all have different radii. But that's not what the problem is asking you for. The problem is asking you to solve the differential equation with these initial conditions. It's just like what we did yesterday. We drew this slope field, which gave us all the infinite possibilities, but then we looked at one particular solution. Well, that's what I want to do now. I want to use one particular solution. This one particular solution tells me that it passes through the point 1, 1. That gives me 1 squared plus 1 squared is equal to c, so c is equal to 2. Which means this particular equation, or the particular function that gives me that differential equation, is x squared plus y squared equals 2. So it has a radius of
4.
root 2. No, the other way around. R squared. Okay? You can handle that, right? So this is an actual AP question. This is from the 2006 AP exam. Problem number 5 in the free response. And I wanted to show you this for a couple of reasons. Number one, I wanted to show you how they commonly combine differential equations. Almost every time they've put a differential equation on an AP test, they pair it with a slope field. And unlike what we did yesterday, where I had you throwing in 10,000 dashes, in this particular problem, they only ask you to draw 8 little dashes. Question number 1. Why do they not ask you to draw any dashes on the y-axis? Say again?
X can't be 0, so there's an ask.
Very good. X can not be equal to 0, so they don't even waste your time with it. What if x is at 1, 0? What's the slope? 1. What if x is at 2? Oh, sorry. What if the point's at 2, 0? 1/2. What about 1, 1? 2. What about 1, negative 1? 0. Good. Halfway done. Let's go to the other side. What if we're at negative 1, negative 1? 0. Negative 1, 0? Good. Negative 1, 1. Negative 2. And last but not least, negative 2, 0. Negative 1/2. Okay. There you go. Not so bad. Then, part B of this problem says, now go and do all the differential equation stuff that we did. I'm not going to do that again because it's not much different than the one we already did, but what I do want you to see is this, which is the grading rubric for this particular problem. And talk a little bit about how they get their numbers. So notice part A, we killed it. Did a perfect job. And notice their comment there, sine of the slope at each point and relative steepness of the slope lines in rows and columns. Meaning, they're not going to measure that to make sure you have a slope of exactly 2. They're going to look to see that the slope is getting steeper as you move up. Or that it's getting more shallow as you move to the right, or it's getting more shallow as you move to the left. That gets you 2 of the 9 points. Remember, these are always worth 9 points. All of part B is worth a total of 7 points. And there's this pesky little thing over here that says 0 out of 6 if no separation of variables. If you don't move the dx to the other side, if you don't cross multiply, if you don't do what we've done on all these problems, it doesn't matter what you did from that point on, you get no points. It seems harsh, but you've been warned. They also throw this little guy in here that says the most you could get is 3 points if you don't include a constant of integration. What's the constant of integration also known as?
C.
Yeah, plus c. The problem is not much different. You cross multiply. The difference here is that some natural logs pop up, but that's okay. You solve for this. You get your general equation here. You plug in and solve for c. You solve for y. Life is grand. The process of the problem is the same as we've done and what you're going to continue to do. What I wanted you to see is what they're looking for on the AP test. You got to separate those variables every time. That's the reason they're called separable differential equations. Problems? This is a slope field made out of students. Some of them are just slope dashes, but you notice the children, kids, people holding hands, they're the particular solution amidst the slope field of infinite solutions. I thought you would enjoy that. And I did not take that picture